Air Force, honored and distinguished guests, good morning, kalimera σας. It is a pleasure and a privilege to have been invited to this very important event and to be able to talk to you about offering a way of thinking and selection with an organization, a user organization that is facing advanced technology choices. What I'm going to present is part of the work that is eventually going to be presented in the 2017 ISABE conference in Manchester, which Cranfield University is co-hosting. I would like to tell you a little bit about our way of evaluating improvements, technology improvements. So my story is going to be very much a techno-economic story, techno-economic evaluation. And I would like to tell you a little bit, first of all, about who we are in Cranfield. Second, about the TERA, techno-economic environmental risk analysis, work that we're doing at Cranfield. Then about a hypothetical choice that a user could be facing on the selection of an aircraft engine upgrade. And I would like to highlight that all the information that you're going to see from this presentation is based on public domain data. Cranfield was set up in 1946, and it was seen as an investment by the British government in terms of taking forward the field of aeronautics. And Cranfield, from the outset, has been a center of research and education in aeronautics. One of the four original areas was propulsion, an area that exists today, and I'm very privileged to be leading it. This is a team of about 250 people that focus entirely on gas turbine engines. We do two things. One is education, one is research. I'm going to be focusing on one of our two areas of research, what we call gas turbine engineering. In gas turbine engineering, the main platform of what we do is our mathematical representation of gas turbine engines. And this is our own inbuilt self-developed program called TurboMatch. And around it, we have a cluster of other capabilities to look at aircraft, to look at ships, to look at power plants, etc. It is this technology that has brought us a great collaboration with Rolls-Royce called the UTC and the AIRC with Airbus and Rolls-Royce Aircraft Integration Research Center. We use this capability to evaluate novel propulsion systems and to evaluate novel technologies that can be applied to propulsion systems. And one of the important areas of development has been the TERA, techno-economic environmental risk analysis. Another area where we have been working on is the area of diagnostics and lifing, another area where there is a great deal of interest from user organizations. Then we also continue to develop this capability, and there's a lot of testing that takes place at Cranfield. Now, the TERA, Techno-Economic Environmental Risk Assessment, this is very much based on the gas turbine. As you can see here at Cranfield, we believe the gas turbine is the center of the universe, and you can see this represented in this picture. In this particular case, we're looking at Hector. Hector is our capability to develop flights of helicopter aircraft. So connected to the gas turbine engine, right at the top you can see this, the body of the helicopter. Then you can see aerodynamic to the left, you can see aerodynamic and mechanical models of the helicopter rotor. To the right, you can see the control systems that we have put in the combined helicopter engine rotor and the helicopter itself. And this allows us to model a variety of missions. And for example, here you have a typical mission that could take place the starting and finishing point is, no surprise, Cranfield University. And in this particular case, we looked at a mission that is about an hour long, approximately about 170 kilometers. And then we can evaluate the amount of fuel that is consumed, the emissions that are produced. This is for a baseline. Then we could look at applying different technologies to this particular helicopter to observe what differences in the mission capability would come about. And it is the use of this particular technology, the Terra, that I would like to go on and tell you now about in application to a civil transport. In this particular case, we're looking at an aircraft operator who is operating an aircraft that is very similar to a Boeing 737 with CFM56 engines, -7 engines. And we are bringing together the aircraft model, we're bringing together the engine model. We have included a blade model to understand the particular impact of the new technology we're going to be evaluating, a technology that is embedded within the overhaul process of the machine. And then to make the techno-economic evaluation of all these. So, if we look to the left of this picture, a thermal barrier coating is a coating that reduces the amount of heat that is going to be transferred from the hot gas, you can see the hot gas flowing at the top, to the base metal. The base metal is the metal part of the blade, and it is the part that constrains the time between overhaul of the gas turbine engine. So by embedding a thermal power coating, we can keep the base metal cooler, therefore reducing from the perspective of creep, the failure of the blade. So in the picture to the right, what we're looking is a potential choice between 6 different thermal barrier coatings. And what we're now going to be assuming is that we are an operator that is flying this particular aircraft, and there is an offer from a particular agent to improve our gas turbine engine by offering this range of 6 coatings. And again, what we see in the picture is that the baseline aircraft, as we have it today, would be able to offer us $25,000 between overhauls. That's typically, for a normal transport, it is about 6 years between the repairs. Then we try the different coatings, and the 6 coating, which is, of course, the more expensive one, can give us a time between overhaul, which is about $40,000. What we are assuming here is that there is nothing else going to catch the engine before this $40,000 and take it out for the need of an overhaul. So what we're assuming is that there is no other limits other than the piece that we are investigating. What we have seen here then is the use of the Terra across a particular mission. So we've broken the flight into something like 100 different segments to assess at each point of the flight what is happening to the engine. And what we have here is the examination of each one of these thermal barrier coatings from A to F. The allowable increase it would give us in turbine inlet temperature if we wanted to retain the same amount of time between overhaul, in other words, to keep maintenance costs the same. And on the right, what we can see is that if we were to use this thermal barrier coating, keeping the same metal temperature, the increase in thrust that the engine could give us, again, assuming that nothing else could catch it. So the top line on the graph is showing us that the thrust could increase from about 140 kilonewtons to 160 kilonewtons in, if you like, the more expensive coating that we could apply. The question we then need to ask ourselves is, what benefit could this give us? And what we see here is the increases in thrust that have been evaluated, assuming that the base metal temperature has been the same. For this particular aircraft, we can see that there is a change in payload up to nearly 2.5 tons of additional payload, again assuming that there are no limits that would not allow us to carry. So assuming there are no structural limits, we're assuming there is nothing else. So the question then we need to ask ourselves, we can carry this additional payload, and what benefit would this give us? So we need then to evaluate the two different types of economic benefit. The first one is looking at the possibility of keeping the blade metal temperature lower, thrust the same, blade metal temperature lower. This is going then to give us a benefit in terms of the maintenance cost of the engine, and this is what we see here. If we use the thermal barrier coating to reduce maintenance cost, to the right, again, we can see the maintenance savings. So if we look at the savings that could be accrued from the different coatings, these are the lines with the blue diamonds. Every year, we could see 100,000 euros reduction per aircraft in terms of the use of the coatings. And we can compute the benefit in terms of the life that is going to be significantly larger. So then one option is to use this thermal barrier coating to extend the maintenance life, to reduce the maintenance cost. In this particular example, the other option is to use the thermal barrier coating to increase the payload the aircraft could carry. These are the 2,500 additional kilograms that the aircraft could carry. And this, again, would give us a different type of benefit. In this particular example, with the numbers that we have used, the benefits are going to be significantly larger. So if we look at the net present value of the increased payload over the life of the aircraft, what we can see is that there is 7 million euros benefit in terms of the most advanced and the most expensive of these coatings. So we have only looked at these two options. We are presenting these. Other options that can be evaluated is, for example, how could we use this thrust to reduce the length of the takeoff run of the aeroplane? That would give it accessibility to more airports. Something else we could do is to use this additional thrust to give us increased capability in a hot day environment, which is a particular concern for many, many operators. So this has been an example of the TERA, techno-economic environmental risk analysis approach that we have used at Cranfield. It brings together the incorporation of aircraft model, engine models. We haven't done it here, emissions models as well. And the idea is it's a technognosy that could be employed by aircraft operators to evaluate the improvements in techno-economic sense that an upgrade could bring. With this, I'm going to close my presentation, and thank you, ladies and gentlemen, for your attention.